Sorry? Lovely. All right then. Just let me know when you need what you need, Steve.
Sorry, I didn't get that, Andrew. It's okay. I'll do a quick start off and then I'll pass across to your good self. No problem.
Champion.
Right. Well, good evening, everyone, and thank you very much for coming along tonight. It's going to be a very interesting talk. I'm quite sure of that, looking even just at the presentation that's on the screen at the moment. Can you all please remember to switch off your telephones, mobiles, I should say. Dear me, isn't it a 70s thing to say that? Please switch off your phones, because there is a penalty for anyone who makes an interruption. Can you also be very aware of where the exits would be in the case of any disasters that may befall us on this evening? And I think as far as the actual lecture is concerned, I don't know, Duncan, would you be willing to give any documentation or paperwork for anyone who wanted to refer to it later?
The presentation is available for public consumption.
It's available for public consumption. Good, that's lovely. Thank you very much indeed. There will, of course, be time for questions. And that, can I pass you across? Apart from having to say, first of all, can you make sure you sign the book and the documentation there? It does have certain benefit to NEMI for all of this to be completed. Right, on that, I'll pass you across to our president, Andrew, and he's going to say a few words about the introduction of who we are, and what we do.
Brilliant. Thank you very much, Steve. So just to say welcome to everybody who's come along, and again, welcome to Duncan as well. It looks to be a very interesting lecture. So our previous lecture was held on the 13th of February. This was by Rod Young, wearing many of his many hats. Good attendance, interesting questions. I think there was a lot of interesting things going on about the valley bulging at the as part of all these dam things. So that was really interesting to hear about. So thank you very much to Rod for that lecture. Hopefully we can take that as a record of the meeting. Our next lecture is actually next week. This has been a bit of a last minute late notice event that's been put together in partnership with the local Northern regional group of the Geological Society of London. That'll be given by Scott O'Neill from Mott MacDonald on understanding the risks posed by mining legacy hazards. And Scott will particularly be dealing with former coal workings. And so that should be very interesting indeed. And our April Institute lecture should be on the 10th of April, and that's with Anna Santos from the Natural History Museum, talking about the bioleaching of critical metals. Again, another very interesting topic. Don't forget, if you want to find out more about our lectures, do please follow us online with the ever increasing back catalogue of recordings we have on offer. And if you want to keep up to date with all of our events and other goings on. We have many things on offer, such as the lecture you're currently at, conferences. If anyone has any conference ideas, then do please get in touch with our institute. We're always very happy to get involved and support various engineering ideas. We have an annual dinner, regular social events and CPD, and the occasional field trip as well. So, of course, the best way to keep up to date with all of our events is by becoming a member. There's plenty of things on offer. We've got the post-nominals, but also sort of making sure we've got an invite to all of the events and the opportunity to get involved with all of our activities. So do please go and look at mininginstitute.org.uk/membership for more information on that. And you can join our ever-growing membership, which is fantastic to see. And with that, I shall pass you back to Steve to do the introduction for Duncan. I know he's been travelling about a lot, so thank you very much for being able to find the time to make it to Newcastle tonight. So back to you, Steve.
Right, thank you very much indeed, Andrew. The next part of the agenda is very simple. Do we have any apologies for absences? I have Keith Hutchinson. Anyone? No? Derek Newton? Okay. Lovely. Thank you. Right. Well, let's not mess around too much now. We've got a situation here now where we have a wonderful speaker of the evening, Duncan McSorland of Honeywell Universal Oil Products, and he's going to talk about choosing the right type of carbon capture technology for your project. Just a little bit about Duncan. He's a business development manager for Honeywell's Sustainable Technology Solutions business, covering carbon capture and hydrogen technology sales for European projects and customers. Duncan gained 25 years of gas industry experience with engineering contractors across all sectors, that's upstream, midstream and downstream, in engineering and sales roles before joining Honeywell UOP in 2022 based in Bracknell. Duncan has an MA in engineering from Cambridge University. Lovely. So I'm not going to say anything more about it at all because the expert is here to tell you all about it himself. So can I hand you over to Duncan McSorland. Thank you very much indeed.
Steve. Thank you. Good evening. It's a real pleasure to be here. I'm talking as a mechanical engineer, but I use that expression tenuously because I've been on the dark side of this business for the last 20 odd years. I'm a sales guy, so I know enough to be dangerous about technologies and engineering though. If you've got any tough questions, you might catch me out, but I can always answer those questions at another later stage, if need be, once I consult my technical peers. So I'm here to talk about decarbonisation through carbon capture and as it relates to hydrogen production. I guess about 45 minutes. I'll keep it fairly swift and we'll do some Q&A afterwards. Okay. Just as a quick introduction, Honeywell, we're a rather large company. You probably know us because you've probably got a thermostat on your wall that says Honeywell on it. We're a big building technologies company. We're also a big aerospace company. In fact, market capitalization of our aerospace business is bigger than Boeing. So Honeywell is a large company, 100,000 employee company. What you probably don't know is that Honeywell owns the world's largest process technology licensor, which is UOP, Universal Oil Products. I don't know if it's an urban myth, but I'm told that you can't fill up your car with petrol or diesel without paying a royalty to UOP. We basically invented refining processes and petrochemical processes. And if you go to look at any gas processing scheme, our gas processing technologies will probably be in there somewhere. Gas sweetening, dehydration, all of these things in the oil and gas business, we are now applying them to the energy transition, which is what this slide says. So we've, like everybody else, we've got a group called Sustainable Technology Solutions within UOP. So those mature technologies in oil and gas and petrochemical processing, we are now deploying them in the fields of energy transition. So whether that's renewable fuels and SAF and renewable diesel, whether it's recycling plastics to make polymer grade feedstock for making ethylene, polyethylene and these kind of things, or hydrogen and carbon capture, what we're doing is taking these mature technologies and applying them to the energy transition. Energy storage is also in there with long duration flow battery technology for energy storage. But today I'm going to talk about carbon capture, both from hard to abate industries perspective and also as it relates to hydrogen production. Yeah, off we go. So, carbon capture technologies. UOP, Honeywell UOP, we can boast the whole range of carbon capture technologies. Some companies have a particular type of technology, we have a whole suite. So what does that mean? We have chemical solvents, physical solvents, adsorbents, and cryogenics and membranes, the whole suite, and all commercially proven, commercially deployed technologies. These aren't new technologies that are low technology readiness level, they're all mature. Apart from one, I should say, this is the advanced solvent for carbon capture. It's a new post-combustion amine solvent. The reason being, if you've got a flue gas with lots of oxygen in there, the old amines that are used for gas sweetening in gas plants, they're not resistant to the oxidative conditions you'll find in flue gases. So the new advanced solvent for carbon capture is a new type of solvent. So that's a new process that we're commercializing. Everything else here is proven. So this funny graph you see here on the right-hand side, what does that mean? Well, what it's saying is, depending on the partial pressure of your CO2 in your feedstock, and depending on the CO2 product specification and pressure, is it a liquid, is it a gas, is it high pressure gas? Depending on these parameters, we can choose which of these technologies can capture CO2, or combination of technologies. So let me just go through these top to bottom. Amine guard is a MDEA, MEA, MDEA, amine concept in pre-combustion capture. We have over 600 units. If you go to a gas processing plant, if you go to an LNG plant, liquefying gas, you need high purity gas before you liquefy it. We use these amines in pre-combustion service to remove sour gas. Benfield is hot potassium carbonate. We invented the Benfield process. You'll see it a lot in syngas applications, taking out CO2 from syngas, quite often in ammonia plants, but also starting to look at this in flue gas application. There are some companies out there using hot potassium carbonate to remove CO2 from things like cement plant flue gas. So we're now by the way, what I should have said, our head office in Chicago, where all of our R&D folks reside, starting to look at Benfield hot potassium carbonate technology as a potential means of decarbonising, taking CO2 out of flue gases. Why Benfield? Well, first of all, let me say, why not Benfield? Why not hot potassium carbonate? We are looking at advanced solvent for carbon capture, the new flue gas capture solvent. We're looking at that, and we know that is better than hot potassium carbonate for removing CO2 out of flue gases. However, some emitters of CO2, I'm thinking municipal energy from waste plants, biomass plants, they've got this thing about amines, nasty chemical, don't want these being emitted near populations. We do stress that our amine emissions are very low, with parts per billion. However, some people just don't want what they consider to be toxic chemicals on site. Either way, we've got the whole suite of technologies, and we can advise. We have something called Separol. It's a Selexol is the physical solvent. Separol is dimethyl ethers of polypropylene glycol. It's a physical solvent that takes acid gases out of typically gasification processes. So gasification of waste, biomass. We're seeing a lot of this at the moment. People trying to gasify such feedstocks to make SAF, and you need to remove that sour gas before you make the SAF. PSAs, pressure swing adsorption systems. Honeywell UOP, we invented them. Over 1,200 in service, typically purifying hydrogen, but we also use PSAs for CO2 rejection. We have Separex membranes. Was it Steve, I think, talking earlier about one of the projects we have on our map of projects. Membranes are very convenient for offshore application. In upstream oil and gas, you want to separate CO2 out of gas. Very easy to do that with a membrane system. It's very easy to operate. No moving parts. It's just a package. It's a module. It separates CO2 out of gas streams. That said, less recovery, less pure CO2. When you're looking at power plants, cement plants, emitters onshore here at the moment, typically you want high purity CO2 before you transport it and store it. Excuse me. And in Ortloff, CO2 fractionation. So we acquired a company called Ortloff. This was born really in the last 2 decades in the US. A lot of fracking projects, a lot of tight gas projects in the shale in the US that you know about. So the whole kind of shale boom over the last couple of decades, there's been a whole bunch of projects where those LPGs and NGLs, they need to be separated from the gas, liquefied, cryogenically fractionated. So a whole bunch of projects we've done there, hundreds and hundreds in the US, separating those LPGs and NGLs from gas streams. And using that experience, we've also been separating CO2 from gas streams by cryogenic fractionation. So all in all, a lot of different technologies, depending on what kind of flue gas you've got or what kind of syngas, what does it look like, what are the contaminants. We take a look at what utilities you've got available. Do you have water cooling? Does it need to be air cooling? Do you have gas? What kind of power do you have? How clean is the power? What's the carbon intensity of your power? Because you've got to look at scope 2 emissions when you're looking at a carbon capture project. So there's a lot of parameters here in choosing your CO2 capture technology or technologies for a carbon capture project. UOP, we are technology licensor, the world's biggest. So what we do is we typically sell you a design and we license the technology, but we also sell, in some instances, packages. A PSA is a package, a membrane is a package. And in some cases, we can also modularize a whole design. And in the gas processing and oil and gas refining businesses, we've delivered about 1,800 modules. Lot to take in here, and you can see this at your leisure afterwards, but whole suite of technologies for carbon capture. So, just looking at typical flue gases, let's say. Looking on the right-hand axis here, starting off at low percentage CO2, like 3 or 4% you'll get out of a gas-fired combined cycle gas turbine plant. And then you might increase that percentage going up to 60, 70, 80% if you've got a cement plant with an oxy-fuel kiln. So, depending on which kind of process you've got, we're seeing that our ASCC, Advanced Solvent Carbon Capture, post-combustion amine solvent, at the lower levels, that amine solvent is the best fit. And then when you get up to higher levels, it starts to be on the cusp of the technologies, where we have a PSA in cryogenics. The PSA is like bulk removal of CO2, gets you from like 20% to 50% CO2 before you cryogenically fractionate it to get pure CO2. And then when you get up to above 50%, it goes to cryogenic only. So these are the kind of analyses we're doing. We're talking to a lot of customers, particularly in cement and steel, where they've got these kind of 20, 25% CO2 flue gas streams. And that's where we're kind of differentiated as Honeywell UOP. We can offer both technologies. We can look at which technology works for that customer. What utilities have they got? And these technologies have got different issues with them. So if you have an amine solvent, you've got to get the NOx and the SOx down to low levels, ppm levels. Otherwise, the solvent's degraded. SOx and NOx and particulates degrade the solvent, and you end up just losing a whole bunch of solvent. You've got to keep topping it up. But you have to top it up anyway in a solvent process, but you want to minimize that degradation. So if you have a solvent process, it does need pre-treatment. It also needs a lot of heat and steam for regenerating the solvent. I'll talk about that in the next slides. Cryogenics and PSAs don't need that, but they need an awful lot of power. And what is the carbon intensity of that power? No point in having an all-electric process if your scope 2 emissions are sky high because you've got very dirty power. So let's assume in the UK that things are moving in the right direction and the grid's going to be decarbonised. So scope 2 emissions, in theory, will be better in the future. In terms of references, so it's always important to we're not just kind of dreaming here. These are real technologies and real deployment cases. The box there on the top right, the black box, shows some of the projects we've done. Just as a bit of a brag, and just to set the scene, about 40 million tonnes per annum of CO2 is captured around the world at the moment, mostly because it's for enhanced oil recovery. Nobody's ever wanted to capture CO2 before for the sake of saving the world because it's an inconvenience, it's a waste product. So most of the projects that exist in black dots, enhanced oil recovery typically, or you're just taking CO2 out of a gas stream and you just want to inject it back into the reservoir. So we've got a lot of projects around the world at the moment. We're capturing over 15 million tonnes of the 40 million tonnes being captured. The recent awards, this is moving a little bit different now. We're getting our new amine solvent. It's not commercially deployed. The amine solvent for carbon capture for flue gases. But we're starting to see projects moving in front-end engineering phase. So I'll talk about some of the projects in a bit more detail, but there's coal-fired power plants in the US. Obviously not in the UK here now because all been decommissioned, but in the US there's some big coal-fired power plants. Duke Energy is a US Department of Energy funded project, 3.6 million tonne per annum CO2 capture. So we're doing the feed with our amine solvent. And interestingly, that plant is going to be converted to gas-fired. So we've also got to design it with a future different composition in mind. But we've also got some gas-fired power plants in the US there being looked at, Crescent and Calpine, big gas-fired power plants. And just as an indication of scale, these combined cycle gas-fired turbine plants, you're looking at, a normal plant, 750 megawatts, even a gigawatt scale. These are millions of tons per annum of CO2, typically a couple of million tons per annum. These are billion-dollar plus projects. In some cases, the carbon capture unit is more than the original installation. You'll get a cement plant, maybe 100 million or 200 million. Honestly, I don't know. I'm not a cement guy. But the carbon capture unit for a million ton per annum CO2 emission cement plant, you're talking hundreds of millions. So this is the magnitude of the industry we're talking about. Very expensive. But this is what we're doing. We've won a project in cement for cryogenic capture and for post-combustion in different services in coal-fired and gas-fired power plants. The amine process. So I don't think there's too many processes engineers here, but what I'm just going to say is this is a typical amine solvent plant. And what we do here is use this advanced solvent that we've developed in conjunction with the University of Texas. And basically what it does is it minimizes the amount of steam required to regenerate the solvent. How a solvent process works is basically you cool it down, you put it through an absorber. This amine solvent absorbs CO2. You get a rich solvent that goes through a bunch of heat exchangers. It goes then through to the regeneration column. We strip out that CO2 from the rich solvent. You need a lot of heat, a lot of steam, and then we export that CO2. And our process is particularly good because we minimize the amount of heat needed and we export it at 5-6 bar pressure CO2. So we know that this is a pretty competitive amine solvent technology. We also have an all-electric design. So when you don't have a source of heat, and let me give you an example. The world's first cement plant carbon capture unit is being deployed at Heidelberg Materials Brevik plant in Norway. But that's only capturing half of the CO2 of the cement plant. And why? Because, well, they haven't got the heat available in the process. So what we're looking at now is all-electric amine solvent plants. So what we do is a couple of things. If you look at our stripper there on the right-hand side, what we do is we compress that CO2 being exported, and the heat of compression, we take that heat and use it to regenerate the solvent, take out CO2 from the solvent. And also, we have a heat pump, so your low-grade heat from your cement process or whatever process you have, we take that heat, and with the coefficient of performance of that refrigerant in the heat pump, we can get some useful steam to regenerate the solvent. Or so not steam, we don't create steam, should I say, we get heat using the refrigerant. So it's a non-steam process. So what we're doing here is an all-electric design to regenerate the solvent. I won't dwell on this slide. You can read this slide at your leisure, but this is the advantages of our amine technology to remove CO2 from flue gases. It's high-pressure CO2 export, low solvent degradation, low demand on the heat needed for solvent regeneration. And we've tested it heavily, so those in the carbon capture business will know that there's something called Technology Centre Mongstad. It's a test centre in Norway that's capturing CO2. But before that, we started life in University of Texas, where the separations research program looked at pilot plants. So this is where the technology for post-combustion amine solvents started. We've then acquired this technology. We've tested it at the NCCC in America. This is in Alabama. It's a coal-fired power plant. We take this slipstream off a coal-fired power plant, and we've tested this amine solvent there over 3 test campaigns. And what it's done is it's proved up our estimate of the performance of this solvent. And we've also tested it most recently at Technology Centre Mongstad. So this is in Norway. It's an oil refinery. I was there with SSC, Scottish and Southern Electric, last month, and EDF of France, hosting them around this site. So what we've been doing there is you know, it takes some flue gases out of this refinery, and we using this amine solvent that we have, it regenerates and emits flue gases which are cleaned up and captures the CO2 for sequestration. About 75,000 tonne per annum CO2. So this is like the gold standard of capturing CO2 testing in the world, TCM. So we know it's a very mature technology given our testing, and what we've done is we've tested it at all sorts of compositions of CO2, because sometimes you have low percentage CO2 in a power plant, sometimes you have high percentage CO2 in a steel plant or a cement plant. You get up to like 20+% CO2. So what we do in this testing campaign, we've done some recycle on the flue gas to make sure we've got up to 20% plus CO2 and see how the performance of the technology works when you've got higher percentage of CO2. And also, this is the important thing, we've also measured the emissions from our absorber. You know, your treated flue gas comes out the absorber, make sure there's no contaminants, make sure there's no amines, no nitrosamines, no ammonia, no aldehydes. So we've tested all of that. So it's basically proven. It's clean flue gas, treated flue gas that you get out of this product. Next technology is our cryogenic technology. So quite simply, if you've got a cement plant or a steel plant, a blast furnace, you've got 20%-ish CO2. What we're doing is compressing that flue gas, putting it through one of our pressure swing adsorption systems, and it kind of takes it from 20% CO2 to like 50% CO2. And your treated flue gas is taken out there, albeit at high pressure, but we can recover some of that energy. And then what happens is our CO2-rich gas, maybe it's 50% CO2, we compress it again, we dehydrate it with our adsorbents, because you've got to get the water out of it before you cryogenically fractionate it. And then you get high purity CO2 liquid product. So this is removing CO2 from a flue gas via PSAs, dehydration, and cryogenic fractionation. Now, TRL, all of this is 9. We've got PSAs in operation, taking CO2 out of streams. We've got 1,400 plus dehydration units. And we've got hundreds of cryogenic fractionation units, including one for CO2 service. So all in all, we say this is TRL 9, piecemeal, but all together, and in cement service, never been done. So this is the challenge we have in the carbon capture world at the moment. It's about pulling all of these technologies together that are proven, but in a different service. And I've just come off the phone, by the way. This technology has been recommended for some EU Innovation Fund applications for cement plants and others, given the relatively low kilowatt-hour per tonnes duty for CO2 removal. And we've also got a project in Germany for a cement plant where this technology is being designed and studied. PSAs, as I say, we've got a lot of experience typically in hydrogen purification, but also in CO2 removal. I'll skip over that slide. But in terms of cryogenic capture of CO2 from feedstocks, hundreds of references in gas processing. As I say, typically is coming from the fracking world in the US, where NGL, LPG, fractionation from gas streams is quite normal. And this is the biggest project. This is taking CO2 out of a gas stream. So a methane gas stream with about 65% CO2. What we do is take that CO2 out of the gas stream by the cryogenic fractionation process. So this is a 2-train system you can see here in Texas. Why on earth did they do this 10, 15 years ago? Well, it was enhanced oil recovery. That's what they used to do in those days. You know, you get CO2 First of all, you want the gas, it's a useful product, and you've got to get the CO2 out of it. And then they use the CO2 injected to go back into the reservoir to get more oil out and gas out of the ground, which has got a kind of perversion around it, of course, these days. So enhanced oil recovery isn't so common these days. We're doing this carbon capture process to make sure we prevent emissions. And then just comparing for these flue gas applications, fractionation versus amines, there's a kind of trade-off. This is a very crude analogy. Maybe about 20% here, 20% CO2 might be an indicative crossover. But what you see here is a red line is an amine solvent plant. So as the concentration of CO2 increases, a little bit cheaper cost per ton. But what you see here for cryogenic fractionation of CO2 massively drops. Why is that? Well, compressing a flue gas is massively expensive. And if you've got largely inert gases and a small percentage of CO2, you're spending a lot of effort compressing inert gases, no interest. So what you want to do is get your CO2 percentage quite high, and then it becomes really quite economical. So what we're saying is in the cement world and the steel world, we're getting to like 20, 25, excuse me, maybe even 30% CO2, and then this cryogenic process becomes really quite interesting to remove CO2, quite economic. And there's also considerations, like I said before, you've got to look at contaminants. Some processes are better for contaminants. You've got to look at utilities available. Do you have heat and steam for an amine process? How much plot space do you have? Part of the problem we've got is a lot of projects for existing facilities, existing power plant, existing cement plant. They weren't built with plot space in mind for a new carbon capture unit. Excuse me. So, yeah, we've talked about flue gases, carbon capture, general application. I'm now just going to talk a little bit about decarbonising hydrogen production. There's a lot of talk about electrolyzers and green hydrogen production. It's very expensive. We are looking, by the way, at green hydrogen. We have membranes. I talked about membranes for carbon capture. We have membranes that we're putting into electrolyzers, which you get green electricity, wind turbines, solar, whatever, and you drive that electrolyzers using that green power, and then you can make green hydrogen, but it's very expensive. Blue hydrogen. So just down the road here, Teesside, you've got BP looking at a blue hydrogen project. So you've got all this methane gas, you reform it, and you capture the CO2. So that's what I'm going to talk about here. Now, just some metrics. Cement industry, 7% of world CO2. So there are some big emitters. Hydrogen, massive emitter of CO2. Now, why are we making hydrogen at the moment? If you work in refining, you need hydrogen for petrochemicals and refining, for hydrotreating, and for various chemical processes. And you need pure hydrogen. So how is that achieved? Typically, it's by reforming, steam methane reformer, SMR. And when you make a kilogram of hydrogen, you make 10 kilograms of CO2. So in the world of producing hydrogen, for various sources, you're making a lot of CO2. So grey hydrogen, 10 kilograms of CO2 per kilogram of hydrogen. It's a lot of hydrogen, a lot of CO2. So what we're doing is taking a typical process in an SMR. So this is an SMR, water gas shift, and then what you do is put this syngas through a hydrogen PSA, and off you go, you make hydrogen. And in the past, the tail gas from the PSA goes through to the steam methane reformer, which is the fuel source. The tail gas is the fuel source, and then you get a flue gas there, which gives you 10 kilograms of CO2 per kilogram of hydrogen. So what we're doing now is we're looking to put our fractionation system to remove CO2 from hydrogen production. So what you get out of this reformer, out of this PSA here, is you get a combination of carbon monoxide, carbon dioxide, hydrogen, methane. And what we're doing is using this fractionation system, to take away the, actually there's a bit of hydrogen here, and we recycle that hydrogen back to product, so you recover more hydrogen out of this process, and then the rest of it you take through the tail gas, through to the reformer heat source, fuel source, and then you get your flue gas. So in hydrogen production, we're looking at our cryogenic production system, capture system, to take CO2 out of hydrogen production. We're also looking at our PSA system to do exactly the same. This is a cheaper way of doing it, but PSAs, less purity of CO2 product, and less recovery. So you're trying to capture as much CO2 as you can. So this is a cheaper way, but less pure way of capturing CO2 out of hydrogen production. And then finally, and this is what most folks are doing at the moment, is pre-combustion amine solvent. And what that's doing is if you've got some steam available, some heat available, you can use that to regenerate that solvent and capture CO2. So there's 3 ways there using our technologies that is decarbonising hydrogen production. And what I haven't said is that in a steam methane reformer making hydrogen, about 60% of the CO2 is in this pre-combustion arena, and about 40% of the CO2 goes up the stack in the flue gas. So all of these 3 things I've just talked about capture your 60%, but they don't capture the 40%. So what we're doing here is we're putting our post-combustion amine solvent on the back. So we're talking to refiners and SMR players, steam methane reformer players, to decarbonise hydrogen production using a combination of our carbon capture technologies. You know, a reminder, green hydrogen's expensive, blue hydrogen's much cheaper, but you need carbon capture. And that's where you need the transportation and storage systems, that's where you need Northern Endurance Partnership down the road here, taking the CO2 and putting it offshore, or in the HyNet area in Liverpool Bay, and taking the CO2 offshore near Stanlow. So blue hydrogen projects are economically viable if you've got government policy incentivising the CO2 capture, and if you've got off-takers of clean hydrogen that are willing to pay that premium. And then finally, the last few slides, there's a lot of information I'm throwing at you here. Autothermal reformers. So these are typically being looked at now for large hydrogen projects. So Teesside here, BP, are looking at an ATR project with Johnson Matthey Technology. They're the autothermal reformer technology player. Same for the HyNet area. It's called HPP1 for SR energy transition. There's a couple of big projects. Kellas Midstream, just down the road, are looking at a blue hydrogen project. So there's a bunch of blue hydrogen projects that are using this ATR technology. And what our Honeywell UOP technology can do is decarbonise that. So we like to think that we're going to have a PSA system in there to purify the hydrogen, and we're offering our cryogenic fractionation system to take out the CO2. And there's three more slides to go. Hydrogen PSA for hydrogen purification. And we can give you thermal grade, fuel grade hydrogen, or chemical grade hydrogen for fuel cells. All depends what kind of hydrogen product you want. Is it like 99.7% hydrogen, or is it 99.99? So these are the kind of things we're helping with our customers, looking at their hydrogen offtake requirements, or maybe it's got multiple offtake requirements, different specs of hydrogen. And we're putting it through our cryogenic fractionation system to capture the CO2, and then recycling it back to the autothermal reformer, so you've not got any CO2 emissions. So this is a recycle process which is really decarbonising hydrogen production. You can see here 0.1 to 0.3 kilograms of CO2 per kilogram of hydrogen. Remember at the start I said typical hydrogen production is 10 kilograms of CO2 per kilogram of hydrogen. So here you're talking about 0.1 to 0.3. One thing I should say is we need to take a little bit of a bleed off of this system here to stop the build-up of inert gases, because otherwise you've got to recycle, inert gases will build up and build up and build up. So there's a small bleed here that's the fired fuel to the autothermal reformer. and that gives you a kind of very small carbon intensity because you've got a bit of carbon in there. And we also have a very advanced system here with a new patented technology which basically takes that bleed of inert gases and gives you effectively a decarbonized fuel supply to your autothermal reformer. So again, this is a recycle system making blue hydrogen, but with almost zero scope 1 emissions. You know, how much CO2 is being emitted? It's almost zero. And then last slide. This is a simpler version, no recycle. We're just sending some of the recycled hydrogen back to product with an additional pressure swing absorption system. So these flow schemes are not theoretical, they are reality. And I say that because this is the world's biggest blue hydrogen project in Texas. So this is the ExxonMobil Baytown project. It's got an autothermal reformer, which is upstream here. This is a Halder Topsoe autothermal reformer. And what you do is once you've got that shifted syngas, you put it through our PSA for hydrogen purification and on-off take. This little piece here I talked about bleeding off the inert gases and giving a fuel source, decarbonized fuel source to the autothermal reformer. We've got our cryogenic CO2 fractionation system, giving you a high purity liquid CO2 product, and then taking it back through on a recycle. We've also got membranes for hydrogen, so we're actually making the autothermal reformer a bit smaller here by taking off some lower purity hydrogen and decarbonizing ExxonMobil Baytown's refinery by giving them fuel grade hydrogen. So this is a real project. This is 7 million tons per annum of CO2 capture, about 1,000 billion scuff per day hydrogen production. So massive hydrogen production plant. And as I say, in the UK, there's a few projects at the moment, one at Stanlow, one at Teesside, and hopefully many more. And then this is the last slide. This is Wabash Valley Resources. Now, this is in Indiana in the USA. This is a waste and biomass gasification project. I believe it's an old coal-fired plant. And now what they're doing is they're gasifying biomass and solid waste. And that produces syngas. And that syngas, combination of CO2 and H2, what we're doing is using our cryogenic capture technology to take CO2 out of that syngas, and then the hydrogen is purified by our pressure swing adsorption system. And we've also got our molecular sieve dehydration system to take water out. So what you're doing is creating blue hydrogen here from gasified biomass and waste. And that blue hydrogen, they're going to synthesize ammonia, so blue ammonia, which Wabash Valley, which is a fertilizer company, is going to make clean fertilizer products. So Honeywell UOP, it's our technology. We're not just selling the technology to this project, we're selling modular supply of equipment for what would be a 1.65 million ton per annum capture project, CO2. So a lot of CO2. Like every project, every problem you have, you've got to work backwards. So you do need that transportation and storage infrastructure in place. You need those depleted oil and gas reservoirs to sequester your CO2, and that's why Liverpool Bay Area in HyNet is a kind of prime source for that, with industrial clusters that are going to send CO2 there. Same with Northern Endurance Partnership up here at Teesside. And there's emitters around here in Tyneside as well, no doubt will feed into that. So you need those clusters, you need the reservoirs, you work back from the solution, you need those repositories of CO2, and then start looking at clusters where you can then have pipelines, lots of emitters, hopefully lower the price of the CO2 transportation and storage. And as Honeywell UOP, we're here to help those emitters with the best carbon capture technology for their particular emissions type. So whether it's a coal-fired power plant, or a gas-fired power plant, or a cement plant, a steel plant, or just anything that burns hydrocarbons and emits CO2. We're talking to those emitters to try to help them meet those challenges. I think that's about it. I've covered a lot of ground here. And it's 45 minutes, I think. We're on perfectly engineered to schedule to perfection. Questions?
Okay, here's your chance now. Ask the questions. There we are. Could you state your name and company you're with, or?
Hello, Ross Freeman from Hatch. Have you any experience of using this technology within the aluminium industry?
That's a good question. No, but curiously, I did meet at a carbon capture conference an aluminium player in the Middle East. I think what they were trying to do actually was decarbonize their power supply. I mean, for example, I'm talking in Africa at the moment to power players that want to decarbonize and then give clean power to mining, to aluminium companies. So Hatch is, they're very prominent in that space, I recall. So yes, we are indirectly talking to some aluminium companies, and I think in the Middle East, I've handed over to my colleagues there that are talking to aluminium players there. In the UK, I don't think there are.
There's one and it's hydro. So
Okay. Yes. Yeah.
So it's mainly on. Sorry, it's mainly to do with the power rather than the smelting of the.
Yes.
Alumina.
Yes. Yeah.
Thank you. Thanks, Duncan. That was excellent. Richard Bernard, I'm an independent. I'll start with an observation first, if I can, and will lead to a question. So if we go back to 2010, so 15 years ago, Longannet Power Station up in Scotland, which at the time was one of the largest coal-fired power stations in Europe, fitted carbon capture and storage to one of its generation streams.
I recall because my previous company deployed that test unit there.
I was part of a team set up by the Department of Energy. I was with the HSE at the time, so team of engineers from the HSE, team of engineers from the Scottish Environment Agency, because obviously it's in Scotland, and the Department of Energy. And we were asked to look at it because obviously at the time we still had a lot of coal-fired power stations in the UK. And we were asked to look at the project from all sorts of angles: safety, environment, efficiency. And we concluded as a team that if you fitted it to a coal-fired power station like Longannet, your efficiency would go down 50%. So, you know, it wouldn't be very... But you would be able to use that asset relatively cleanly. And that was the paper that we gave back to the government that commissioned it. And the government's reply, after they sat on it for 6 months, was, but coal's very dirty. Why would we want to do that? But, you know, this was a way of using an existing asset and actually, you know, using it in a way which was carbon sort of efficient. So I guess my question is, you mentioned politicians a few times. I'm sure your company works with politicians across the globe.
We do.
How do you go about, obviously you want to sell your products, you're a commercial organisation, but how do you go about sort of educating those politicians that sometimes the solutions which feel a bit wrong can be the right solutions? Because there's no magic bullets in this space. There's lots of good solutions, as I said, but no magic bullets. And as I said, to be dismissed as a politician, well, coal is dirty, didn't seem like a great answer to me, because we proved that actually, if you decrease the efficiency, you can make it work.
Yeah. No, it's a very good question. So we have a government relations group. We've got a colleague of mine, Willie Kutsia in Bracknell, is our government relations director. And we have a bunch of folks in Brussels, the obvious place for government relations folks to reside on the continent. And what that team does, the GR team, lobbies and advocates policy to such stakeholders. I mean, give you an example. We might be thinking about cement, where you've got processed CO2 from calcium carbonate. Now, there's no way you can there's nothing you can do about that. So why not be able to use that as CO2 feedstock for utilization for making SAF? At the moment, generally making SAF, you want biogenic feedstock. But why not calcium carbonate produce CO2 in cement production? So that's the kind of thing that, I mean, certainly the cement players, that's what they want to lobby about, as an example. So we do lobby governments and institutions, and our GR function looks at, as I say, policy and advocacy, and that's their full-time job. And there are other factors as well, just international politics. We are a US company, and also with our friend in the US now as president, that also has an impact on matters. So not only do we have to think about the kind of the process side of things, and the technical side, but also the political side, and the fact that we're a US company trying to work in Europe.
Anyone else? There wasn't any online at all, David, was there? No questions online.
Yeah.
Well, there we are. A very, very complicated subject, I must admit, and I can't say that I fully understood everything, but I got a good idea. But thank God we've got people like Honeywell doing this sort of thing for us. But in saying that, thank you very much. Can I pass it across to David Bobbs here, who's going to give a vote of thanks on behalf of the North of England Institute.
Like you, that was quite technical, but very, very interesting, Duncan, and thank you very much for that. We've had a number of discussions here from all different angles of carbon capture. We've had BP here, you probably down at Teesside. We've had John Bluyas talking about some of the work that they do at the Sciences Department. We've had people from Blythe, CO2, absorbing minerals. We've had some fantastic discussion, and this is great to hear from a vendor who's actually supplying into that industry. Very interesting indeed. And of course, it's interesting from your point of view. By the sounds of it, you spent a lifetime in oil and gas getting oil out, and now, of course, you're working in trying to get that CO2 back into the ground again. So that's very interesting. And from my point of view, I wasn't aware that there was a number of different techniques that you could use. Personally, I was aware of amine, and the difficulties with amine, the chemistry, the temperature, but it's very interesting to note all of the other ones, the cryogenics, etc. But the bit that I was quite surprised at was when you talked about 1 kilo of hydrogen and 10 kilos of CO2. I mean, that's quite, we're all talking about hydrogen and how we're going to make it work. And that's quite an interesting fact, isn't it? Although you did go on to say, of course, that there are new mechanisms coming in place. So fascinating. And I think from everybody's point of view, we would like to thank you in the normal way for your time, your energy, and your excellent presentation. Thank you very much.
Yeah, pleasure.
Right, thank you very much, David. That's wonderful. And well, here we are at the end of another very, very interesting lecture. Thank you very much indeed. And all it has for me to say is the next meeting. We're having a joint lecture in Thursday the 27th. That's next Thursday, which I'm sure you'd like to come along and see. It's understanding the risks posed by mining legacy hazards. By Scott O'Neill of McDonald. I'm sure that'll be a very, very interesting subject. So please do come along. We need your support, and please take note. Sorry? Oh, there's another slide. Right. Come on. Oh, right. He knows how to do it. And the April Institute lecture, again, was on the 10th of April, and that's going to be Bioleaching of Critical Metals by Anna Santos from the Natural History Museum. So again, you know, you're not going to have much time to do your gardening or anything like that, because I expect you all to be here listening to what we have to offer. So thank you very much. There's not much else to say other than, can you make sure you do sign the books and the sheets at the door, and take great care when you're going home. So there we are, the next meetings. Thank you very much for attending tonight, and I look forward to seeing you next Thursday.
Thank you. So if anybody's got any questions one-on-one, I'm happy to, or thoughts, happy to hear them.
So your friend in the States, you know, drill baby drill, is going to help you?
Well, what I think is going to happen is that